Hey guys, welcome back. Wanted to do a quick video on a topic that I heard on a YouTube video that I was listening to. The guys were talking about the relative merits, among other things, of adding additional counterweights to improve the performance of a astrophotography system, and I wanted to look into that. Sounded interesting. I just wanted to take a look at that, at least as it relates to my system. There are so many different astrophotography system setups that are possible that one great idea that one person might use for their system may not be applicable to your system. And in this case, I wanted to do a few calculations to figure out if the concept of adding counterweights would in fact translate into improved performance. Now, what do we mean by that? Well, first of all, for those of you not familiar with these kinds of German equatorial mounts, their counterweights are located down here on a counterweight bar. In my case, I've got one 11-pound weight and one 17-pound weight, and the purpose of the counterweights is to balance out the weight of the telescopes on the other side of the right ascension axis. So in essence, the overall or total mass of the telescopes on this side of the right ascension axis, their center of mass times the radius or the distance from the center of mass to the right ascension axis, has to be equal to the product of the counterweight mass times its distance to the right ascension axis. So we've got to have a balanced system. If we don't have a balanced system, then the poor little torque motor inside the mount here that's rotating this system about the right ascension axis is having to do a lot of extra work. So having a balanced system is a critical element to a good performing astrophotography setup. But all right, the more mass we add and the farther away that mass is from the right ascension axis, the greater the mass moment of inertia is. And it's the mass moment of inertia that works in tandem with the applied torque that determines the responsiveness of the system to guidance commands. For example, here on the left side of this equation is the torque generated by the torque motor for the right ascension axis, and on the right hand side we have the mass moment of inertia I of the total system, all right, times the angular acceleration that we can achieve with that torque, all right, plus some other effects of torque that are working against us generally. For example, stiction. There's a good bit of stiction in my mount. That is, if you were just to go push against the mount with the clutches off, you'd find there's a little bit of resistance there. And if you look back to the previous video, you can see a little test I did where the mount will come to rest at a non-vertical angle because of the inherent stiction inside the mount. Another contribution is a torque, gravity torque, that comes about from not being in balance. So I'm sending my mount out to be hypertuned. That should take the stiction down to a minimum number. It won't be zero, can't be zero, but it'll be a lot smaller than it is now. And that will also help me to be able to achieve an accurate balance, which will help me to basically reduce as much as I possibly can that term in the curly brackets there. Now, if we were to solve this equation for alpha, which is again the angular acceleration, we see that we have the torque from the motor, which has to overcome, first and foremost, the gravity torque from being out of balance, any stiction inside the joints, and then whatever torque is left over from that, we scale that down by the mass moment of inertia. So if the mass moment of inertia of the system is high, then the resulting acceleration, angular acceleration we get, is low. That's a sluggish system. The system won't be able to keep up with, if this in an extreme case, it won't be able to keep up with the commands generated by the guiding software as part of the auto guiding package. So remember, this guidance scope, the guide camera, that's talking to software that is trying to maintain the location of a selected guide star at a given point, at a given location within the sensor of the guide camera. And so it's sending commands to the right ascension axis in this case to either speed up or slow down in order to maintain the location of that guide star. And in fact, when I look at my guiding graphs that I get from PhD2, the biggest challenge, the biggest problem I have in guiding is actually in the right ascension axis. It's not the declination axis. All right, good polar alignment can pretty much achieve minimal demands on the deck axis, but I find that right now my effectiveness in guiding, and therefore the quality of the photos I generate, is really being dictated by the right ascension axis, and that's why I'm particularly interested in anything that can improve the performance with respect to the right ascension axis. All right, now we'll have a much more responsive system if we can maximize the available angular acceleration. And again, we do that by hypertuning, perhaps by good balance, and to the extent possible by reducing the mass moment of inertia. And that's what this little presentation is about. Can we add counterweights to the system and improve the mass moment of inertia? Well, if we increase the number of counterweights, that means that we have to take this weight. Now imagine this stack getting larger, so I'm going to add another plate onto the stack. We have to move this stack closer or further up the bar in order to maintain balance. Well, two things are happening here. One, we're adding mass down below, which it tends to increase the mass moment of inertia, which is bad. But we're also moving that total mass up closer to the right ascension axis, which is good, squared. All right, and here's why. A typical equation, a baseline equation for the mass moment of inertia, is mass times the distance to the axis that it's rotating about squared. So if I double the mass, well, I'm going to have to cut the radius, r, the distance to the right ascension axis in this case, I'm going to have to cut it by 1/2 in order to maintain the same balance condition. Well, in this equation, that's like multiplying by 2 and dividing by 4, which is in effect like dividing by 2. So in other words, by doubling the mass, the counterweights, I can in effect cut the mass moment of inertia in half, at least of the counterweights. Now that's the thing. The OTA, all right, the two telescopes up above, well, they contribute rather significantly to the total mass moment of inertia, as does the mount itself. So the mass moment of inertia of the OTAs, the mass moment of inertia of the mount, and the mass moment of inertia of the counterweights are all contributing to the total mass moment of inertia that the torque motor has to work on. So there is some benefit. We expect some benefit by increasing the number of counterweights, but is it enough to worry about? And that's what I want to look at. All right. So what I've done is gone back through the geometry of my particular system with the weights of the different telescopes, their locations relative to the right ascension axis, the counterweights that I have, their location relative to the right ascension axis. Gone through a series of calculations and came up with this curve for my system. All right. On the bottom axis, we have the cost. All right. How much do I have to pay? Now we're talking about buying additional counterweights. All right. And then on the vertical axis is the percent reduction in the overall mass moment of inertia of the system. So think of it, you can think of it as a reduction in the mass moment of inertia of the system, or as an increase in the available torque, if you want to think of it that way. All right, starting from scratch, which is where I am right now, I've got one 11-pound weight and one 17-pound weight, and so that's our starting point. If I add one 11-pound weight, according to the web, it costs me about $55 to do that. That will give me about a 13% or 12% reduction in the mass moment of inertia. Okay, so it's not insignificant. It's not great. It's not insignificant. If instead I bought one 17-pound mass and didn't buy the 11-pound mass, one 17-pound mass costs about $80, and that takes me up to about 16% reduction in the mass moment of inertia. Or I could buy one of each and get like 21%. But eventually I'm going to get to a peak up here where I simply can't get any more. There's no point in buying any more weights because there's a line of stupid here. If I were to buy additional counterweights that took me past the line of stupid, in effect what would be happening is I could spend $350, get a 20% reduction in the mass moment of inertia, which I could have gotten by simply buying one additional weight for $135. So there's a line of stupid that we don't want to cross. But that's not all. It's a little more complicated than that. In addition to the line of stupid, there's a line of possible. And by that, I mean there's what's physically possible to put on your mount. In my case, let's focus on the upper edge of the counterweights that we're talking about. We may be adding a counterweight, but there'll be a top edge. Then let's keep our eye on that. This line of stupid comes about, and this point on the graph comes about when we've added so much additional weight that this top edge comes up, up, up. And remember, every time we add weight, we're moving the overall we have to move the overall center of mass of all those weights up in order to maintain balance of the scope of the telescope and the guide scope above. All right. So as we add weights, as we add counterweights, that oval, the top edge of those counterweights is moving up. So as we add more and more weight, that line is moving up, and the line of stupid happens when that top edge moves past this line. Now, you can probably already see a problem here. All right, what that really means mathematically is that for every bit of additional counterweight mass that we add after that, we are also having to add additional counterweight mass on the bottom, so to speak, to balance out that counterweight mass that's above the yellow line. Well, that's stupid, obviously, hence the name line of stupid, but it's also not possible, hence the line of impossible here, line of possible. We can only put enough weight, enough counterweights on this bar until they bump into this stop here. Okay, that's the end. We can't put any more counterweights on the system at that point. So the one thing we always have to be able to do is to be able to balance the system. It is possible to buy more counterweights. However, what you will find is you won't be able to keep the system in balance, and we always have to we can't have more counterweights and not enough space to achieve balance. So that's where the line of possible comes from. Now, in my case, roughly speaking, this line of possible, this constraint line, is about 6 inches or so below the right ascension axis of the mount. Well, going back to what we were talking about, if I add one 11-pound counterweight, then the top edge of the now stack of 3 counterweights is 7.9 inches below the right ascension axis, which puts it about 2 inches below this green line. What that means is that yes, I could buy an 11-pound weight, and I would be able to put that weight on this system and properly balance the system. So that's doable. So I can get a 12% reduction in the mass moment of inertia. That's not a problem. What if instead I bought the 17-pound weight? Well, now that top edge, according to these calculations, is 6 inches, 6.1 inches below the 6-inch line, which means it's only barely possible. All right. In fact, if I go in and make more accurate measurements once I get the mount back, I may decide that this is not possible at all. But let's just say, for the sake of discussion, that it is possible. All right. That somewhere in here, this line of possible comes in about right here. That I would be able to buy the 17-pound counterweight, put it on the system, and be able to balance the system with that weight on there. All right. Now, if I were to buy one of each, though, that top surface of the counterweights would be at 3.6 inches below the right ascension axis. In other words, somewhere about right in here. And that's not possible because I'm going to run into this physical stop here that will prevent me from doing that. So yes, I could go ahead and buy that extra counterweight, but there's no way I can put those weights on here and make this system balance out. So that would certainly be stupid as well. All right, so for me and the system I only have one or two options. It's either buy an 11-pound counterweight or buy a 17-pound counterweight. And the maximum benefit that I can get out of this is about 16%, all right, at best. Let's look at an alternative. What if I were to eliminate the weight of the guide scope up here? All right, that does a couple of things. First of all, obviously it eliminates weight, but also it's the weight that's farthest from the right ascension axis and therefore has the greatest effect per pound on the mass moment of inertia. So that's a pretty big step. So in effect, you replace this guide scope and all of its weight with a simple little attachment that goes right here at prime focus. The imaging camera, the T2i, or this webcam, would fit into here. All right, and then my current guide camera would be unplugged from this guide scope and plug into the side. And there's a little mirror in here that takes a bit of light that's coming down the main imaging scope. It gets deflected out and sent up the viewing axis of the guide camera, and that's what it uses to perform its guidance duties. All right, so that is a significant benefit, but there's another benefit, which is since I'm reducing the mass on this side of the right ascension axis, that means I get to take the two counterweights that I do have and move them up the counterweight bar, which reduces the mass moment of inertia even further. All right. Now let's go back to that curve that we were just looking at. We decided that at best I can add a 17-pound counterweight and get maybe a 16% reduction in the mass moment of inertia. Anything beyond that, any other options of adding mass, I simply can't balance the system. All right. Now, if I were to take the guide scope off, buy a off-axis guider for about $220, there is a significant reduction in the mass moment of inertia, a 62% reduction in the mass moment of inertia. Now that is a significant benefit. All right. There is a potential risk here, though. I mentioned there's a line of stupid just about everywhere you go in this hobby, and I may just have crossed it. And this is it. You've got to be able to have a guide star in the field of view in order to lock onto, have enough signal to noise ratio to be able to lock onto and use for guidance during the imaging session. Well, the guide camera has a very small chip, and now when you couple that with a very long focal length telescope, I think it's 22,350 millimeter telescope, you have a very narrow field of view. All right, which means basically there needs to be a star in our galaxy that's bright enough to see, all right, that also happens to be in line with the galaxy typically that I'm imaging during one of my imaging sessions. The ASI 120 monochrome camera made by ZW Optics is a nice sensitive camera, and I have not had to operate it at maximum gain for the type of for its use with the guide scope that I have. So I may be pushing that camera to its limits of sensitivity, and in fact I may well find that there are some targets that I can't find a guide star, that I just won't be able to perform the auto guiding that I need to do in order to achieve the long exposures that I need in order to get good images. So that may be the line of stupid that I crossed with this little approach here. I've ordered the off-axis guider. I'll plug it in. We'll have maybe an opportunity for another video at a later date. But what have we learned here? Well, first of all, we have learned that adding additional counterweights to a system can improve the responses of the system by reducing the mass moment of inertia, but only up to a point. All right. The numbers that I've been using for my system, and I suspect it'll be for most systems out there, the best case improvement is on the order of a 5 to 15%. And honestly, I've concluded looking at these numbers, and certainly for my system, it's just not worth the cost. There's just, for the amount of cost, whether it's $80 or $55, the 10 to 12 to 15% improvement I might get is just not worth the improvement. If possible, a much more cost-effective way of improving the system responsiveness, again by reducing the mass moment of inertia of the system, is to replace the separate guide scope with an off-axis guider. Maybe. Okay, that has problems, and the problem is that with a long focal length system, you better have a really sensitive guide camera, otherwise you're not going to be able to find a guide star to guide on, and that may be the line of stupid that I just crossed. And finally, we've learned that with my scope out for repairs, I've got like way too much free time. All right, well, that's it for now. Just wanted to make a little video about the the notion that adding counterweights improves system performance, and there's a bit of truth there, but as with most things, there are some limits there that we need to be mindful of. I hope you might find this a little bit useful, and I'll talk to you later.